Okay, shall we start? So welcome to the Wald Lecture II. The speaker is Martin Barlow from UBC. As usual, if you have questions, please either type the questions in the chat box or please click the raise hand. Then I'll ask the speaker or I'll unmute you. Okay, so the title is low-dimensional random fractals. So Martin, please start.
Okay, thank you for the introduction. So let's just review very quickly, what we saw in the first lecture. Our ultimate aim is to study random walk and the heat equation on random fractal graphs, particularly examples which are arising in statistical physics. And the motivating example here is the critical percolation cluster in ZD. And we saw that we have a good understanding of random walk on some specific families of deterministic fractal graphs. But the proofs, which I didn't go into, use very strongly special features of the fractal, in particular their symmetry. So now we want to develop more general methods which will have a chance of working for random fractal graphs. And just as a sort of way to set things up, it's useful to sort of put things in what we could call a context of an axiomatic framework. And this way of viewing the subject was pioneered by Grigorian and Telch in a couple of papers in 2001 and 2002. Which is to identify relationships between various possible properties of a fractal graph, and then hope that these can be verified in a specific example. So that's a bit vague. Let me now explain by first example, transience and recurrence. So we've got an infinite locally finite weighted graph GW. Remember, a weighted graph is a graph with edge weights or conductances on the edges. And we fix the vertex x and recall that the effective resistance from a point x to infinity is the limit of the resistances from x to the boundary of a ball of radius r. And we'll say that the graph satisfies property T if it's transient, and property Rf for resistance finite if the effective resistance from a point x to infinity is finite. Then the Doyle-Snell theorem that I mentioned at the end of the last lecture can be restated by saying that the properties T and Rf are equivalent. And of course, the result's useful because property Rf is in some cases easier to verify than property T, and also because property Rf has clear stability properties under perturbation of weights, whereas property T does not have those clear stability properties. If we change the weights, we change the random walk. There's no coupling between the random walk on the graph with weights W and W prime, but the resistances in those graphs are bounded above and below by constants. So Rf has better properties than T, and that's what makes the Doyle-Snell property useful. So now let's look at some other graph properties which are going to be of interest to us from the point of view of random walks on random fractal graphs. So first of all, we're going to look at the volume growth of the graph. In other words, how big balls are. And we say that G satisfies the property V alpha if the measure mu W of balls is bounded above and below by constants times R to the alpha. If we're in the case of natural weights, that means that the size of balls is also bounded. Well, if the graph has uniformly bounded vertex degree and we've got natural weights, that's saying the number of points in balls is also bounded above and below by R to the alpha. Now for a property we haven't met before, Rn, which is resistance in annuli. So what we do here is we look at the effective resistance between a ball of radius r and the ball of twice the radius complement of the ball of radius 2r. So we're looking at the annulus between those balls. We're looking at the effective resistance across those that annulus. And this property here says that this is bounded above and below by constants times r to the beta times mu w of the ball. And the graph G satisfies HK alpha beta if it satisfies the sub-Gaussian estimates that we saw held for the Sierpinski gasket with parameters alpha and beta. So n to the minus alpha over beta on the diagonal if x is equal to y, and then the same kind of decay that we saw last time held for the Sierpinski gasket. One difference from in the previous lecture, the Sierpinski gasket's got lots of triangles, so it's not a bipartite graph. But in general, we have to be able to handle bipartite graphs, which is only a minor nuisance, but it's a nuisance. And the technically easiest way of doing it is to look at the sum of Pnxy and Pn plus 1xy. On a bipartite graph, one of these terms is going to be 0. So we have these three properties. And here's another property which is going to be important for us, which is the elliptic Hamack inequality, a property which may or may not hold for a graph. So Hamack inequalities originally came in complex analysis in the 19th century. In a very important paper, Moser in 1961 proved an elliptic Hamack inequality for the solutions to a certain kind of PDE. And that work was foundational in establishing regularity for those PDE and is basically now a standard technique in the theory of partial differential equations. So we say that a graph satisfies the elliptic Hamack inequality, EHI for short, if there's a constant CH such that whenever we take a point x, a radius of a ball, and a non-negative harmonic function in BXR, then when we look at the function over the ball of radius r over 2, the maximum is, well, the ratio of the max and the min is less than CH. And this is initially stated as a sort of analytic result. There's no exact probabilistic simple counterpart, but roughly speaking, what it forces is good mixing of the Markov chain X inside the ball of radius r over 2 before it leaves the ball of radius r. So let's look at a picture here. Remember that we're writing tau xr for the exit times from balls. The boundary of a ball are the points in the complement of the ball which are adjacent to a point in the ball. We take a point y in the boundary and we look at the harmonic function, particular harmonic function, which is that the random walk x leaves the ball at the point y. So here's the point y. We're looking at the function, the probability that the random walk, when it leaves this ball, does so at y. Then here's the ball b prime. The elliptic Hamack inequality is saying that the function h, the ratio between the max and the min of the function h over this ball is bounded by some constant, by this constant ch. So if, for example, we were in the situation where the walk is moving much more rapidly horizontally than vertically, then from a point here, the random walk would be rather likely to leave at y, and from a point here, the random walk would be very unlikely to leave at the point y, so the elliptic Hamack inequality wouldn't hold. We'll be looking at later some examples of graphs for which the EHI, other examples for which it fails. So here is the basic result of Grigorian and Telch, which I've simplified a bit. So let's look at an infinite connected weighted graph, which is satisfying the local regularity condition that edge weights are essentially bounded below. So we can't have edges in the graph which are really small weights. Then we have the following equivalence. The heat kernel or transition probability bounds HK alpha beta are equivalent to the elliptic Hamack inequality plus the annulus resistance estimate plus volume growth of size alpha. And from now on, I'm always going to assume that graphs are connected and satisfy this local regularity condition. So if we want to prove the transition density bounds, what we need are basically these three things. We need bounds on the number of points in a ball, if we're working on a graph with natural weights. We need to be able to calculate effective resistances across annuli, and we need the elliptic Hamack inequality. A remark in passing, well, let's note that if the HK alpha beta estimates hold, then the transition probabilities from going from X to X satisfy this condition that they get bounded above and below by n to the minus alpha over beta. And so the graph GW is recurrent if and only if the parameter alpha is less than or equal to beta. When alpha is strictly smaller than beta, we call this the low dimensional case, and one has a simpler theorem. We need another definition. I'm saying that the graph satisfies a point-to-point resistance estimate with a parameter gamma if the effective resistance between the points x and y grows as dxy to the gamma for all x and y in the vertex set V. And here is the simpler theorem due to myself, Thierry Coulomb and Takashi Kumagai. If alpha is strictly smaller than beta, then we can prove the HK alpha beta estimates if we first of all have the V alpha estimate and then the point-to-point resistance estimate beta minus alpha. So before we I say a little bit about the proofs of those results, let's just see how they help us, how we can use them to get the transitivity density bounds on the Sierpinski gasket. So remember, for the Sierpinski gasket, we had the fractal dimension log 3 over log 2 and the walk dimension log 5 over log 2. And recall that a triangle of side 2 to the n contains about 3 to the n points. So it's not hard to verify the condition that, well, the boundary, the size of a ball of radius r goes like r to the df. So the condition volume growth of size df holds. One has it, of course, immediate. Well, no, one has it for the origin or for the corners of triangles and balls of size 2 to the n, and then a little bit of shuffling and interpolation is needed to get it generally. The next thing we need is the resistances between points on the Sierpinski gasket. And here I'm going to use a well-known result in circuit reduction in electrical theory called the gamma delta transform. So if you've got a triangle like that, it's electrically equivalent to a sort of Y like this with appropriate resistances on the 3 branches of the Y. And what equivalent means is that if I take one of those triangles out of a circuit and put in a Y, the response, electrical response of the circuit is not changed by that perturbation. So using this transform, one can reduce the Sierpinski gasket. We start off with a level 2 triangle like that. We use the transform to replace each of the upward triangles by a Y or a downward facing Y. Now we've got 2 resistors in series here. We can replace them by a single resistor here of appropriate size. We get this. We now do the same thing to the upward triangle in the middle to get this. And then we use the transform to get back to a triangle here. And I haven't gone into the sizes of these resistances, but if you start off here with resistors of size 1, you end up here with resistors of size 5 over 3. And iterating this process, one finds that a triangle of size 2 to the k with unit resistances can be reduced to a single triangle with resistances size 5 over 3rd to the k. And with a bit more work, one can then prove that the effective resistance between points in the Sierpinski gasket is bounded above and below by constants times dxy to the dw minus df. So we verified the condition RPP dw minus df, and we've verified the condition V df. And so if for the moment we just go back to the theorem BCK, what that tells us is that then the Sierpinski gasket satisfies the bounds HK, DF, DW. And I've given, of course, I've missed out some details, but let me say that the argument that we have here, even with all the details put in, is much easier than the proof in the original proof of this result in my paper with Perkins in 1988. So now let me say a little bit about how we prove the result that V alpha, R and beta, and EHI give you the HK alpha beta estimates. And so at the end of the first lecture, I gave you a result on the round trip time in a finite graph. The round trip time is the effective resistance between the points times the mu W of V. So this is basically saying that the time to do something is the effective resistance times the volume. And so what that suggests, and of course, is that the crossing time of the annulus Bx2r minus Bxr should on average be the effective resistance across the annulus times mu W of A. Under the assumption that we have V alpha, then mu W of A is about, well, the mu W of Bx2r, mu W of A, and mu W of Bxr are all about the same order. And so we end up with the crossing time being of order r to the beta. And let me say that the smoothness of harmonic functions given by the elliptic Hamack inequality allows this rough calculation to be made rigorous. And so what one deduces is that the exit time of Bxr started at a point x is of order r to the beta. Since the process moves the distance about n to the 1 over beta in time n, it follows that if we set r equals n to the 1 over beta, then the probability starting at x that xn is still in this ball, it's about 1. I'm writing bounded above and below by a half. And we can write that as the sum over y and bxr of pnxy. The Hamack inequality suggests that these functions should not change too much as we vary y. And so in other words, that pnxy should be of the same order as pnxx. So if we accept that, then we get this equation relation here. Summing over wy over y and bxr, we get mu w of bxr times pnxx. So in other words, we get that pnxx, and hence therefore pnxy should be about r to the minus alpha or n to the minus alpha over beta. So what we see is that the resistance, the elliptic Hamack inequality and the resistance and volume estimates lead us to the following estimate on the pnxy when x and y are not too far apart. And as is clear to you, I've missed out a lot of details, but the rough calculations here explain why the various indices that we're have the values that they do. And using the elliptic Hamack inequality and other things, one can fill in the various gaps in this argument. So that's the sort of bound for x and y reasonably close together. We also want bounds when x and y are a long way away. And I'm just going to give you a quick hint of how we get off-diagonal bounds. The first step is, as we saw in the first part of the argument, we have what we call a near diagonal lower bound. Diagonal would be x equals y. Near diagonal means when the distance between x and y is relatively small. And then there's a very general method in PDE called chaining, and we can use this to obtain the general lower bound. So supposing we take points x and y distance r apart, and we want to bound ptxy for some t. We choose an n depending on r and t, and then we choose a sequence of n balls going from x to y, where the balls are radius r over n, and the distances between the points zk are of also order r over n. So we have a picture something like this. And then what we're going to do is we're going to look at the event that x goes from little x to little y in time t, and bound that below by the probability that x goes from here to the first ball, from the first ball in time t over n, from the first ball to the second ball in time t over n, and so on, and then finally from this ball into y. We use the Chapman-Kolmogorov equations to do that, and if we stick those estimates in, we basically find that we end up with an estimate e to the minus n times t to the minus alpha over beta, t to the minus alpha over beta coming from the final step. And when we choose n in the optimum way, we rather surprisingly end up with the correct estimate. It's a bit surprising, perhaps, because we seem to be throwing an immense amount away, requiring x from travel, the process to travel from x to y along the particular sequence of balls that we've chosen. But the long-range bounds hold in the case when it's rather hard for the process to get from x to y in time t. And if they go at all, they basically, the process needs to go as quickly and as uniformly as possible from x to y. So although we appear to have thrown away a lot, in the end, all we have done is we've perhaps lost some constants in the exponential. So that is a very quick, oh, let me just say, for the upper bound on, we use a different kind of chaining involving looking at the process jumping distances r over n. So I've given you a very quick sketch of the proof of the Gregorian-Telch theorem. Now let's look at the low-dimensional or strongly recurrent case. And recall that the graph satisfies RPP gamma, point-to-point resistance RPP, if the effective resistance between points x and y goes like dxy to the gamma. And that the theorem BCK tells us that V alpha and RPP beta minus alpha is equivalent to HK alpha beta. So we say that a graph is strongly recurrent if there is a constant P0 bigger than naught, such that this relation holds. So let's just look. We have a ball Bx and Bxr, and tau xr is the exit time from the ball of radius r. Ty is the hitting time of the point y. And so what we're saying or requiring is that starting at the center of the ball, the process hits any point Ty with probability bigger than P0 before it leaves the ball of radius r. It's easy to see that Z is strongly recurrent. Z2 is recurrent, but not strongly recurrent, because this estimate will involve something like a log, 1 over log r will be the probability of hitting. If you have the strongly recurrent property, then if you've got a harmonic function in Bxr, and you've got a point y in Bxr over 2, then a simple use of the Markov property, the fact that h of x is a martingale, tells us that h of y is bigger than P0 times h of x. So we have a very nice, quick relationship between h of y and h of x, which gives us the elliptic Hamack inequality quite easily. So the RPP gamma property proves the elliptic Hamack inequality. It also proves, also in the first lecture, I gave you an estimate on connecting resistances and hitting probabilities, and using that connection, RPP gamma implies strong recurrence. So V alpha and RPP gamma together give the volume growth of radius of order alpha and the elliptic Hamack inequality. With a bit more work, one finds that these also imply the annulus resistance estimate. So these properties together give fairly straightforwardly the 3 properties in the Gregorian-Telch paper, and hence give us the proof of theorem BCK. So This part of the talk has been, I've gone a bit into the details of proofs because I felt it was helpful to see get some idea of the sort of basic ideas behind these arguments. Shortly, I'm going to go on to random graphs, but first of all, let's just look at the question of what alpha and beta are possible for a graph satisfying the bounds hk alpha and beta. And remember the Gregorian-Church theorem that we saw. So the first thing that we can say, so supposing we've got an infinite graph with natural weights and it satisfies hk alpha beta. The first thing we can say is that alpha has to be bigger than or equal to 1. The graph is infinite, it's connected, and so there's a path from x to the boundary of the ball of radius, b delta bxr, which is of length r, so it contains at least r points, so alpha has to be bigger than or equal to 1. Then for beta, there are some general random walk bounds, the Kahn-Varopoulos bounds, which tells us that on any graph which does not have exponential volume growth, or graph with polynomial volume growth or conditioning like satisfying the condition V alpha, the distance that the process moves in time n is only a little bit bigger than n to the 1/2. The bounds hk alpha in beta imply that the distance between x0 and xn is bigger than n to the 1/beta infinitely often. And so we're looking at those two inequalities here. One deduces that beta has to be bigger than or equal to 2. So alpha is bigger than or equal to 1, beta is bigger than or equal to 2. Finally, the resistance estimates, the resistance between these two sets has to be less than or equal to r because there is a path of length r joining these two sets. And so we deduce that beta minus alpha is less than or equal to 1. So we have these three relations on alpha and beta. And a result I proved in 2004 is that there are no other restrictions. So for any pair alpha and beta satisfying these conditions, there exists a graph which is satisfying hk alpha beta. So here's a picture of the sort of alpha beta space of the possible graphs. The graphs ZD are the ones in with red squares. The Sierpinski gasket and Sierpinski carpet are these ones marked in green here. And the light blue shaded region are the graphs which are strongly recurrent. Recurrent but not strongly recurrent would be the graphs which are on the border of the two blue regions, and transient graphs are the ones which are in the slightly darker blue. So this is the collection of graphs that we have: transient, recurrent but not strongly recurrent, and strongly recurrent. And we've seen that the strongly recurrent are the easiest to handle. And so with this understanding of deterministic graphs, we can now turn to looking at random graphs. And I'm going to start with, we can first of all think about critical percolation clusters. That's not the easiest case of random graph, but let's look now at the critical percolation in high dimensions. So it's been proved in that case that theta of PC, the probability that the cluster containing naught is infinite, is 0. And so we have a continuous phase transition, and there are no infinite clusters. Nevertheless, large finite critical clusters are reasonably common. So if you look at a box of size 2 to the n, with high probability, there is going to be a cluster with diameter of roughly order the size of the box, in other words, order of diameter 2 to the n. If you now look at a bigger box, very often this cluster Cn will fail to connect with the large cluster in the bigger box Qn+1. So as you go outwards, looking at bigger and bigger sequence of boxes, you see a collection of larger and larger big clusters, but each big cluster typically will fail to connect with the big cluster at level 1 up from that. And a sort of quick way of thinking about things, there's a large cluster near you in the graph, but you're not in it. Well, on any finite cluster, the random walk is not going to have very interesting long-run behavior. In the end, it's just going to settle down to an equilibrium distribution on that cluster. So to get some sort of handle on what random walk looks like on large finite clusters for finite times, Keston developed the concept of the incipient infinite cluster. Keston did it first of all for trees and for Z2, and van der Hofstadt and Geray did it for high dimensions. So this is how we construct the IIC. We look at the cluster C0, which contains naught, and we condition on that cluster being big in some way, such as that we look at the event fx, which is the cluster C0 connects 0 to x. We look at an event G describing percolation inside the box minus mm to the d, and we define p tilde m of G to be the limit as x tends to infinity of the probability under PC that G holds, conditioning on fx. Of course, it's not clear a priori that this limit exists. That's the theorem of van der Hofstadt and Geray in high dimensions. Then the conclusion is that the laws p tilde m are consistent and extend to give a law p tilde on clusters in ZD. And under p tilde, the cluster C0 is infinite as we wanted it to be. So we're going to denote it C0 tilde, and we call it the IIC, or incipient infinite cluster. And it's expected that other natural ways of conditioning C0 to be large, like requiring it to connect to the boundary of a box or to have a large volume, should give the same law p tilde. So physicists thought about this in the early 1980s, and let me define now the spectral dimension of an infinite graph. It's minus twice the limit as n tends to infinity, p2n xx over log 2n. So if pn xx goes down like n to the minus gamma, then the spectral dimension is going to be 2 gamma. And they chose the spectral dimension of this so that the spectral dimension of ZD is D, not D over 2. The heat kernel bounds HK, DF, DW implied the following relationship between DS, DF, and DW will hold in that case. And two physicists, Alexander and Orbach, in 1983, conjectured that the spectral dimension of the IIC should be 4/3. I've restated this conjecture for mathematicians because, well, it's a physics conjecture, and so made sense in their terms. But since they didn't actually have the concept of the IIC, they couldn't have sort of stated it as the way that we have here. So rather surprisingly, they're conjecturing that whatever the dimension, the spectral dimension of the IIC should always take the value of 4/3. So why did they think that this conjecture might hold? So a general idea in statistical physics is of upper critical dimension. You have an upper critical dimension in your system, DC, and when D is bigger than DC, global phenomena cease to be dependent on the dimension. For percolation, the upper critical dimension is 6. And at PC, at the critical probability, there's just enough probability of an edge being open to allow large-scale connected structures of open edges. If we increase the probability P a tiny bit above PC, we're going to get an infinite cluster. So at the critical value, particularly if we know that theta of PC is 0, we've got large finite clusters or structures which are almost enough connected to be infinite. But the structures that we get, these large-scale structures are going to be thin. If they were too thick, they would already connect and give us an infinite cluster. And when D is bigger than DC, these large-scale structures don't self-intersect except locally. So they don't see the true dimension of the space they're in. This is the intuition. And so, in fact, these large-scale structures should be close to being fractal trees, and so should be similar to the IIC for percolation on the binary tree, which I'm going to be talking about in a moment. It was known, lots of calculations on trees are easy, and it was known that the spectral dimension for the IIC on B had 4/3. So the AO conjecture really has two parts. The first part is that when D is bigger than DC, the spectral dimension should be 4/3, but they also made the bold conjecture that this should actually hold for all dimensions, so D bigger than or equal to 2, rather than D bigger than 6. It was sort of confirmed by numerical simulations in 1983. Computers now are much bigger and are much faster, and it's pretty clear now that the AO conjecture doesn't hold for low dimensions, but there's no proof. So let's look at the IIC on the binary tree B. So here's a picture of the beginnings of the binary tree. And we're going to look on critical percolation on the binary tree. PC is a half. And I'm going to condition on there being a path from the root here up to level R. Then the IIC is the cluster. So we first of all condition on there being a path up to level R. Then we let R tend to infinity. And the IIC is going to be the cluster containing the root. So the first part of it might look like this. Now, Kasten analyzed the structure of the IIC on the binary tree. And let's take Z to be a, sorry, this statement here is, this statement here is right. We look at a critical binary branching process, Zn, then the IIC on B actually has the genealogical structure of this branching process conditioned to live forever. But Kasten also showed it can be constructed in a following more direct way. We choose a path from the root 0 to infinity at random, and we call this the backbone. And then we run unconditioned critical Galton-Watson processes from each point of the backbone. Each of these processes will become extinct almost surely, so all the branches are finite. And the IIC there on B is therefore a one-ended tree with large finite branches. So if we go back to the picture that we saw here, you'll notice that something is slightly darker red than the rest. This is supposed to be the backbone here, and then each of these branches coming off it here is a critical Galton-Watson process, which will therefore ultimately become extinct. So working with Yarai, Kumagai, and Slade, we began in 2007 to look at the problem of proving the AO conjecture for the IIC in high dimensions. So theorem BCK tells us that if we can prove that balls have size alpha and the effective resistance from a point X to the boundary of a ball goes like R to the beta minus alpha, then we would be able to prove the bounds HK alpha beta. But we're looking at a random graph, and there's no possibility that bounds of this kind can hold for all X and R. In fact, what we found is 0 plays a special role in the IIC, and we couldn't actually obtain estimates on general balls BXR. We had to make do with estimates on balls rooted at 0. So let's set up some terminology now for random graphs. We have a probability space and a family curly G of infinite connected random subgraphs of ZD. And we are going to assume that the origin is in the vertex set for all omega. Let's write rho omega for the effective resistance between 0 and the ball of radius surface of the ball of radius r minus 1. And this estimate holds here. And we're going to write px with a subscript omega for the law of the random walk started at x, and p omega n xy for its transition density. So we're going to say a ball is lambda good if the volume of the ball is r to the alpha with an error of lambda or lambda to the minus 1, and the resistance out to the ball of surface of radius r is bigger than lambda to the minus 1 r. So this is an event which may or may not hold. And we say the random graph satisfies a condition H alpha if the probability that balls are lambda good is bigger than 1 minus lambda to the minus q for all r bigger than or equal to 1, and I should have said lambda large. So we can't be sure that all balls are good, but what we have is the condition that with high probability, a particular ball of radius r is lambda good. And then we have the theorem BJKS, initially for some parameter values done by myself, Jarai, Kumagai, and Slade, and then generalized by Kumagai and Masuni. So we suppose that the condition H alpha holds, then P almost surely, the spectral dimension of GW is 2 alpha over 1 plus alpha, and the walk dimension is 1 plus alpha. I should say here that in this case, yeah, okay, yeah. Okay, yeah. So what this theorem has done, we initially start at the problem of looking at random walks on random graphs. What this theorem is doing is in some sense taking out the random walks from the problem. If we now have a random graph, the problem of calculating the spectral dimension is reduced to the problem of containing volume and resistance bounds. This is hidden here is the fact that we're in the strongly recurrent case. So now let's go back to the first example, which is the IIC on the binary tree. It's got the genealogical structure of a critical binary branching process conditioned to live forever. So we know that the expected value of Zn is 1, and the probability that Zn is bigger than 0 goes down like C over n. So the conditional value of Xn of Zn, given that Zn is bigger than 0, goes like Cn. And so if Zr is bigger than 0, we expect that the size of the ball of radius r should be about the sum, well, it's the sum, exactly the sum from 1 to r of Zk. And there are r terms here. The last r over 2 of them are all about size r. So we get approximately r squared for the size of balls. And in fact, it's not hard to turn this using Keston's decomposition into a rigorous argument and show that under the IIC law, the size of the probability that the ball is ball of radius r has size between lambda to the minus 1 r squared and lambda r squared. That should be e to the minus c lambda, sorry, not e to the minus c r. So the volume of the part of the condition H2 holds. We also have the problem of resistances. And a key property is that if we look at the number of individuals alive at time r who have offspring alive at time 2r, let's call that yr, then yr, we look at the individuals alive at time r, and we look at the indicator that the branching process starting from that of individual should be alive at time r. And this is equal in distribution to a binomial random variable with these parameters. There's a missing bracket there. And this is about Zr, and this is about a constant over r. So this random variable yr is of order 1. So we have about yr individuals at time r. We have order 1 individuals at time r who are alive and who have offspring at time 2r. Using standard electrical arguments, one then obtains a bound that the resistance between 0 and the ball of radius 2r is about R, which is what we wanted. And so for the IIC on the binary tree, one has df is 2 and dw is 1 plus df. And you'll notice that dw is bigger than df here, so we're in the strongly recurrent case. So that was the binary tree. The same program has been carried out in a number of other cases. In 2008, in this paper, we did it for critical long-range oriented percolation. I've explained some of the random walk part of the paper. The other part is using the LACE expansion to obtain the volume and resistance estimates, and that's a significant amount of work. At the same time, Gordon, with others, obtained similar estimates for invasion percolation on the binary tree, slightly different model than the IIC on the binary tree. Kumigai and Musuni looked at long-range percolation on Z, and Cosma and Nachmius looked at, will prove this result for critical percolation, standard critical percolation in ZD when D is bigger than or equal to 11, or the result will also hold for long-range percolation when D is bigger than 6. With Robert Masson, I looked at the uniform spanning tree in 2 dimensions. Again, here dW is 1 plus dF, but now the fractal dimension is 2 over a number kappa 2, which is the loop exponent, growth exponent of loop array's random walk in Z2. That should be not Z3. And more recently, Angel, Croydon, Hernandez, Torres, and Shirashi have carried out this, have done this for the uniform spanning tree in 3 dimensions, and you get a similar pattern, but now the volume growth is 3 over kappa 3. So for a variety of these models, we've been able to calculate the spectral dimension. In all these cases, you're either looking at a tree or at a random graph like long-range percolation in ZD, which is pretty close to a tree. It's still quite a challenge to look at some things which are far from trees, like critical site percolation in 2 dimensions. So here is a picture of critical site percolation in 2 dimensions. You have each little hexagon is either white or red, and this is a picture due to Mike Kostrom. Now, as many of you are aware, there's been spectacular progress on understanding 2-dimensional models in statistical physics, and it's known that the boundaries between the red and white regions converge to a continuum process, SLE 6. And using this connection, many exponents have been calculated for the IIC for the percolation process. For example, the dimension of the cluster is 91 over 48, and the dimension of the boundary of the hole's famous conjecture of Mandelbrot is 4/3. As I remarked, better computers since 1930 or 40 years of computer improvement since 1983 now show that the AO conjecture is unlikely to hold in low dimensions. But perhaps a bit surprisingly, what physicists are so good at making conjectures, there doesn't actually seem to be any generally accepted conjecture on what the spectral dimension for the 2-dimensional critical percolation should be. To calculate DS, one needs electrical resistance properties of the IIC, and these are harder to obtain than the geometrical properties, particularly geometric properties of the boundaries, which have been obtained from the SLE theory. And one may also need to know the length of the shortest path in the cluster across a box of side R, another quantity the SLE theory does not seem to give. So if you're looking at resistances across this picture, it involves sort of more global sort of structure. The electric current is going to be moving along a number of these challenges, a number of these channels. SLE tells us what the boundaries are looking like, but it's not telling us or it doesn't seem to be telling us how all these channels fit together. And so it doesn't seem to be going far enough as to give us, at any rate, easily electrical resistances of this critical site percolation. So that's the situation for one of the open problems is critical site percolation in D equals 2. And that's the end of today's lecture. Next on Friday, I'm going to be talking about higher dimensional fractals and higher dimensional random fractals.
Thank you very much, Martin. Oops. Sorry. Thank you very much, Martin. So questions, comments, please either type on the chat box or click the raise hand box. No question? Okay, then I have two questions. One is a kind of naive question. So there are various random geometry which are recurrent but not strongly recurrent. For instance, the random walk on the UIPT.
Yes.
Do you think there is a way to analyze it using the strongly recurrent method? I mean, by approximating through the, by approximation or whatever?
I would, as far as I would, it seems not. I mean, as you, in fact, I'm going to be saying a little bit about UIPT at the end of my third lecture. It seems that the methods I've been talking about there, you're going to get log R type errors in a box of side R. And as far as I can tell, the methods that I've been talking about just don't work in that context. I mean, it's not to say that it's impossible that they work, but no one has made them work, and I would be wouldn't be surprised if they don't work.
Okay, thank you. And another question is more specific. So in the lecture, you explained how to obtain the resistance point-to-point estimate for the Sierpinski gasket.
Yes.
Do you have any simple method to obtain such resistance point-to-point method, point-to-point estimate for the two-dimensional Sierpinski carpet?
No, I have not thought about that question. It may be, I mean, one knows about the resistances across squares.
Yes. So resistance, annulus estimate you obtained with rich bus, but
yes. So that would give you a bound one way.
Yes, that's right.
And then it's possible that by sort of approximating, going into the point and sort of, I don't know. I'm going to say not. I don't know how to do it. I'm not saying, unlike your previous question, it may be possible, but I don't know.
I see. Well, I mean,
it's an interesting problem suitable for a master's student, perhaps.
Okay. Well, I mean, of course, using elliptic Hamack one can get it, but without using just.
Yeah.
Okay.
Yeah.
Yeah. Okay. Thank you. So, any more questions? Please either click the raise hand or type on the chat. Okay. If not, let's thank Martin.
Thank you.
So Martin's third lecture will be given on Friday, the same time. Actually, that's just before the opening ceremony of Tokyo Olympic. So please come back. So thank you very much. So
thank you.
I think, yeah. Okay. Thank you. Thank you, everyone. Bye.
Right. Goodbye.